Hello folks. All right, well, last time we used Lex to look at the tokenizing side of things. This time around we'll take a look at Yacc for the parsing side, and that will let us put things together and hopefully have it all make a reasonable amount of sense. So again, Yacc is yet another compiler, or it's upgraded version Bison, which is actually what winds up getting run, but that's okay. This is what allows us to express the parsing rules for our language, and the C code that we associated with it is what allows us to do things like perform the detailed analysis of the source code program that we're reading, or it allows us to generate the translated version, if we want to produce machine code, or if we want to produce a translation into a different language. So this is really the one that lets us get some active work done, if you like, with our Lex and Yacc playing. So between the two of them, we can go through and perform some pretty amazing things when it comes to working with a language based on a formal grammar for it. Alrighty, where did I want to take this? So the sequence, again, this is what we ran through in the Lex side of things. Yacc is kind of a middle stage here where we run Lex to set up the tokenization, we run Yacc to set up the parsing, we compile the pieces together to produce whatever our analysis tool is actually going to be. So the two files are going to be, or the two parts of this are going to be pretty closely interrelated. The structure is going to look familiar in that the Yacc file is divided up into 3 chunks, and again separated by the %%, just like in the Lex file. And again, that first section is going to be used for definitions, for C libraries, prototyping, variables, that kind of thing. The second section is going to be used for the actual parsing rules. And then the third section is going to be used for a main routine and for the implementation of any functions that we prototyped back in the top section. So this is going to look very much like the Lex files that we looked at earlier, right? If we've got a C section where we're doing our prototyping and our hash includes and declaring any variables, we're also going to have a bunch of definitions of data types and specifying which tokens are of which type in this top section as well. We'll have a bunch of parser rules, so the context-free grammar rules, if you like, and the C code that goes along with that to perform the semantic analysis and to perform any translation that we want. And then at the end, the main routine and any other functions that we want. So maybe we'll pop over and take a quick look at a little sample program. So back to that really simple one we did way back when we said we had a language that just consisted of a print statement and an integer inside curly brackets. Right? So this was that really simple Lex one that we took a look at. If we want to go through this and take a look at the Yacc file, again, we'll have a section at the beginning where we do our hash includes. This one, we're going to have the YYWrap and the YYWrap that YYWrap and YYError that we created in the Lex file, plus a YYLex that's actually going to get auto-generated for us as part of the whole Lex Yacc compilation process. We're going to specify what the top level non-terminal is. So again, if I wanted to say that my top level non-terminal was top level or start or program or whatever I want to call it. So %start and whatever I want as a name for that top level non-terminal. I'll get into looking at the data types for our tokens in just a sec, and we'll provide a list of all the token types and associated data type with them. If you recall, in the Lex side of things, we were saying that the yylval for each of them has a specific data type. Each token can have a specific type of yylval. This is where we decide what those types are. In this union, we're going to go through and provide a list of all the available data types, give each one a name, and then for every token type, we're going to specify which data type that is. In this particular example, they're all going to be longs, so I'm just going to give a list of all of my token types here. And if you recall, we had a token type for integers, we had a token type for that print keyword, a token type for the open curly bracket, a token type for the closed curly bracket. And then we'll give a list of all of the non-terminals supported for the language. So in this language, we've pretty much got the program as a whole. So that's our top level non-terminal, if you like. And then maybe we'll have statements that are just the abstract, if you like, for our print statements, where we've got the keyword print and an integer value. So we can associate data types with each of our non-terminals. And again, so we'll have this one line listing our, or maybe multiple lines if we've got different data types, but a line representing our tokens and a line representing our non-terminals. And then a suite of grammar rules that say, okay, for each of these non-terminals, what can they be composed of? For this particular language, the program as a whole is just an open curly bracket, a statement, and a closed curly bracket, where that statement is a print and an integer value. So this section is what we'll be expanding to include all of the different context-free grammar rules we want to support for the language. And then at the bottom, we'll go through and again have the main routine and any other C functions we decided that we wanted to create for our own use as part of this. So the main routine is basically focused on having this parse that again is auto-generated and carries out all of the parsing process for us and is going to return a 0 or non-zero value depending on whether it worked or not. And ultimately we're probably going to have our main routine return that. But again, if there are things that you want to do to set things up, and if you're doing things like creating a symbol table or some such thing, you can initialize all that sort of thing or have functions that run ahead of time to initialize whatever you want initialized. If you've got cleanup to do, you can do that after the parse completes, or if you've got reporting you want to do afterwards, you can do that here. So this main routine can actually be quite complex, but it's all geared around that parsing process itself. So again, this is the basic structure for our Lex file, or pardon me, our Yacc file. And again, this is pretty much summarizing what I was saying there. Our yylex is auto-generated, yrr and ywrap are coming from the .lex file. We use that same sort of % open curly bracket, % close curly bracket to wrap the C header section up at the top. And again, just because the Yacc program is expecting syntax like that to tell it when it's entering the C header section. You can access variables that were created in the .lex file, that were declared in the .lex file. So you do that by, in that section, specifying that, for instance, I want to access row and column or some such thing. You specify that they were declared in that Lex file. And again, you can prototype as many additional C functions as you like, as long as you remember to give implementations for them as well. So, in the Lex file, we said that every token could have a yylval associated with it. And you could have all sorts of different data types for a yylval. So one token type might use strings, another token type might use ints, another token type might use some complex struct. And it's here in the Yacc file that we have to specify what the possible data types are, associate a name with each of them, and then eventually specify which tokens use which types. So yylval is a variable with whose data type is a union. So again, that basically means it can be any one of these data types, but only one of them at a time. So I'm going to say that maybe the available data types for my tokens are either an int, in which case I'll refer to it as an ID, a char star, in which case I'll refer to it as a str for a string. It can be this finfo struct, in which case I'll refer to it as a fract. So maybe I'm representing fractions or something like that. So you give a list of the possible data types for yylval and give a name for each of them. And then off in the Lex file, when we want a particular token to refer to the int type, we say yylval.id. When we want it to refer to the char star type, we use yylval.str. right? So those data types are defined here and used over in the Lex file. Now, the nice thing is that here in the Yacc file, we don't need the yylval stuff. We're going to be able to just refer to them by ID or str or fract or whatever it might be. So we've come up with this list of what the possible data types are for my tokens. Now we want to go through and say for each token type, which one of these things is it? So if you've got a token type named integer, then you have to specify that, okay, this is the type of data it's going to use. Or if I've got a token type named identifier, maybe this is the data type I want it to use. And so for each of the tokens that you use, you specify which data type from that list it's using. And again, over in the yylval, you're using things like the yylval.num, or pardon me, over in the Lex file, you're using things like the yylval.num to access the appropriate data type for that token type. Here in the Yacc file, you can just straight ahead use num or use fract or whatever it might be. So we'll come back to that later. Then the other half is we need our non-terminals. So the rules for all of the non-terminals in the program. So you've got this top level non-terminal, say program or whatever it might be, that describes the program as a whole. Maybe you've got non-terminals for, I don't know, an if statement. Maybe you've got a non-terminal for a block or for a statement list or for an individual statement. So all of those non-terminals need to be declared, and you can associate data types with each of them just like you can with the tokens. So for the non-terminals, you go through and list for each of them a type. So you can say the non-terminals that are of type int, so you'd use %type int, and then the list of the non-terminals that are using that data type. And if you've got a bunch of non-terminals that are using char stars, again, you can do the same sort of thing. So just like with our tokens, we go through and identify the types for every one of our non-terminals. So we've just got a list of the non-terminals over here. And you specify what the top level sort of starting point for your non-terminals are. What's the generic top level abstract name for your program as a whole? So I quite often just use program. So if we want to go back to our example there, oops. Again, I just had the one type for our union, so all our yylvals in this one are just going to be longs. So all of the token types are longs, and our two non-terminals are going to be longs. So I'm going to have a non-terminal for the program as a whole and a non-terminal for our statements. And again, within the grammar rules, we'll go through and specify what each of those things is made up of. Now, there are additional things that we'll get to and make use of later on for all of the different operators that you wind up using in your program or in your language. You can go through and specify whether they're the associativity. Is it left to right or right to left? So you can actually say, if you've got operators like a different kinds of assignment operator and different kinds of add and subtraction, different kinds of comparison operator, for each of them you can either use %right and list all of the ones that are done right to left, or %left and all of the ones that are done left to right. So that gives the parser a little bit of extra information for it to handle as it's going through your expressions. So all of these things are in that declarations, that top section. Then in that second section, we've got all of the different grammar rules. And so again, for each of them, it's the non-terminal, a colon, and then what it's made up of. So that can be a list of other non-terminals and tokens. Now, you can associate blocks of C code with each of these as well. You can say, if you decide that this is the next appropriate rule in the derivation, then run this C code. If this is the next appropriate rule in the derivation, then run this C code. So you can use these blocks of C code to have certain actions carried out when a rule is applied. Now, in the early stages, we'll just look at examples where we don't actually run any C code. We just check to see if the derivation works. Just try and get an accurate and a viable parsing of the source code. Let's see. So again, we just have maybe a couple of simple grammar rules. A program is made up of an opening curly bracket, statement, closing curly bracket. A statement is a print and then an int. Right? So you can have something nice and straightforward. Again, if we wanted to, we could provide additional rules in here. Now, if we decided we wanted to improve our program, make it our language, and make it a little bit more flexible, maybe I decide that I want to be able to have multiple statements inside a program. So instead of just one print, we could have a whole bunch of prints, kind of one or more prints. So maybe we decide that what we'll do then is, let's add here, our program can be made up of, let's say, a list of statements instead of just a single statement. So I'm going to need a statement list as an additional non-terminal. And in my grammar rules, I'll need to provide a rule for what a statement list is made up of. So I could say that a statement list is made up of either a single statement or it's made up of a statement followed by a statement list. Right, so we can go through and come up with an improvement to our grammar, right? Expand our language, and hopefully this still accepts. What was the name of my sample program? Sample prog, okay. So let's try running this thing from our sample program that had just a single print in it, and things look okay. Let's edit our sample program and make 2 print statements and see if it still works okay. So see if our new rule still works out. So let's try that again. And yeah, we still seem to be okay. Let's check and see if it actually detects if something's broken. So if I, for instance, forget the integer part that's supposed to go along with a print statement, yeah, figures out that we've got a syntax error. This isn't valid, syntactically valid for the language. So it does indeed appear to be working out. Obviously, there's a lot more testing we'd want to do, but the basic idea seems to be okay. All right. Now, within those chunks of C code that we can associate with things, we can actually take a look at the value that's associated with a token, and we can associate values with non-terminals. We can do things with those values. And the way it's done is by using the $sign and the data type name and which component we're looking at for a rule. So if I've got something like a rule, statement is made up of an identifier, an assignment operator, and an expression, and then I've got some block of C code that I want to associate with that, then in that block of C code, I'm going to refer to identifier as essentially $1 if you like, assignment op as $2, and expression as $3. And I can go through and access the data associated with that particular token. So if there was a string associated with my identifier token, then I can get at it. I can refer to it as $, and then in the angle brackets, str and 1. Right? Again, the 1 refers to the position in the list. The str refers to which of those union data types we were interested in, and the $, is basically just doing our evaluation of that. So we could go through and do something like, for instance, do a printf %s on whatever the identifier name was. I just found identifier blah as part of an assignment statement. So you can start doing all sorts of fancy things. Let's say I decided that I wanted to come up with a translator from the current language into some new programming language. Then here I could say, well, let's print out what this would look like in the new language. So I'd look up the name associated with the identifier. I'd look up, whatever the new language was supposed to print out in terms of an assignment operator, and I'd look up a translation of whatever the expression had to be. So again, this expression is a non-terminal. It's going to get processed by further rules down the road here. But I can go through and have print statements in here that actually translate the individual components based on the data that's stored in their associated data type from that union. So you can get quite sophisticated in terms of what you do here. All right, again, the tool that we're creating, it could be a compiler, it could be a static analysis tool, just going through and checking to make sure that the syntax is all correct. It could be a code formatter, right, just to reformat things in the exact same language but nicely printed out. It could be an optimizer that just goes through and tries to rewrite it to be more efficient. Anything we like, right? So whatever it is we're doing in the C blocks associated with the rules is what we want to take place in transforming the old code into whatever the new code is going to be. And again, we can make use of whatever data types we want, whatever prototypes we want, whatever variables we want, as long as we declare them in that top section and have the function definitions, function implementations produced in that bottom section. So sky's the limit here in terms of what we want to do. All right, again, I think we already covered this, but the actual parsing begins with that call to yylval, which invokes an attempt to go through all of those different context-free grammar rules. Well, it goes through all of the Lex to produce a tokenization, and then goes through all of those context-free grammar rules to try and come up with a valid parsing of the source code. And again, if you've got an unambiguous grammar, then there's only one valid parsing. So you can ensure that you're going to get the translation that you should based on that idea. All right, there is lots more to consider, but that kind of wraps up the general intro to Lex and Yacc.